Okay, greetings. Welcome to discussion on week two. So today we'll be going through three different examples which are related to transfer function, poles and zeros of the system, and related topics. So let's come to our first question. So we have to determine the transfer function, poles and zeros of the system, and the steady state value for a unit step response of this differential equation. So to solve this question, we need to know what is the Laplace transform of, say, nth derivative of a function of s, sorry, a function of t. It is s n f of s minus summation of k from k equals to 1 to n s of n minus k. So this is k minus 1th derivative at 0. So the governing equation is given here as y double dot of t plus 6y dot of t plus 5y equals to u of t. Taking the Laplace transform on both the sides, uh, we obtain this expression s square y of s minus s into y of 0 minus y dot of 0. This for the first term. For the second term is 6 into s y of s minus y0 plus 5 into y of s equals to u of s. Now we will substitute zero initial condition as that is the prerequisite for the definition of transfer function. That's how we define transfer function. So y of 0 is 0 and y dot of 0 is 0. So the above expression becomes 6 into s into y of s plus 5 y of s equals to u of s. Taking y of s common and bringing u of s in the denominator and doing some algebraic transfers, we get the transfer function as y of s by u of s, s square plus 6s plus 5. So uh, this is our answer A. So let us name this as g of s. If we factorize this g of s transfer function, we get factors as 1 and 5. So s plus 1 and s plus 5. What are poles? Poles are the uh, roots of denominator polynomial. So to find poles, to find the poles of the transfer function here, we will take the denominator transfer function and equate it to 0. So that means s plus 1 would be 0 or s plus 5 would be 0. This implies the poles of given transfer function are s is equals to minus 1 and minus 5. So this is the answer to B part. So we are looking at how do we obtain the transfer function, poles and zeros of the system, and steady state value for a unit step response of this particular uh, differential equation. So we took the Laplace transform, and then we substituted zero initial condition here to finally obtain the transfer function. Then we took the denominator for polynomial and equated it to 0. That gave us the poles of the system. Since the numerator is a constant in the transfer function, there are no zeros in the system or transfer function. Now, to solve the third portion, the unit step response of this polynomial, let us use the final value theorem. So here, as time tends to infinity for f of t, we will get same value when s tends to 0 in the limit of s into f of s. So if we write the output of our transfer function to the unit step response, we can write 1 over s square plus 6s plus 5 multiplied by s because of the final value theorem multiplied by 1 upon s, which is due to unit step input. So cancelling the s out, we can take the limit of the remaining expression. So if we take the limit of s tending to 0, y of s, uh, we can just put s equals to 0 here. So it will be 0 plus 0 plus 5, that is 1 over 5. So to summarize this problem, we are looking at calculation of transfer function, poles and zero of the system, and the steady state value. So we took Laplace transform of the equation here and then substituted the zero initial condition in order to finally obtain the transfer function. Once we obtain the transfer function, we can look at the denominator and equate it to 0 and solve for poles of the system. Here, since there is a constant in the numerator, there are no zeros in the system. To solve for the steady state value, we are using final value theorem, where a limit in time can be converted into a limit in S domain. So when s tending to z, when we utilize this final value theorem for the unit step response, we will get the final value as 1 over 5. Now coming to the second question, here we have to find the system's response uh, under zero initial condition and make certain comments, or we'll see some observations. So here the given system y double dot of t plus 3 into y dot of t is equals to u of t. Taking the Laplace transform, we get s square y of s minus s into y of 0 minus y dot of 0 plus 3 into s y of s minus y of 0 is equals to u of s. Now we substitute 0 initial condition, y of 0 is 0 and y dot of 0 is 0. So we get s square y of s plus 3 into s into y of s is equals to u of s. So the transfer function is ratio of y of s by u of s, which is we are calling it as g of s. This here becomes 1 over s in bracket s plus 3. So uh, what is different about this system than the previous example? Here the poles are s is equals to 0 and s plus 3 is equals to 0. That implies s is equals to 0 and minus 3. So this pole is on the left side of the complex plane, and this pole, say minus 3, and this pole is at the imaginary axis. So such systems are unstable, and in certain cases it's also referred as a marginally stable system. So now uh, coming to the calculation of response of the system. So u of t is given as sine of under root 3t. Laplace transform of the sine term, that is Laplace of sine omega t, is given by omega upon s square plus omega square. So y of s would be g of s into u of s, which is in our case we have 1 over s in bracket s plus 3 as the transfer function, and multiplied by omega here is under root 3. So we have under root 3 divided by s square plus under root 3 square, which is 3. So let us write y of s again as s s plus 3 and s square plus 3. Right. So now we want to take inverse Laplace transform. So that we can get the expression for the response of the system in time domain. So we can write it as a over s, which is the first factor, plus b over s plus 3 plus c into s plus d over s square plus 3. And here if we find the uh, coefficients a, b, c and d, then we would be able to take the inverse Laplace transform of these terms. So what we will do here is we'll multiply, let me divide it into two parts. We'll multiply both the sides of this expression, let me call this as e, by uh, s. So and then we'll put s equals to 0. So here when we multiply this term by s, this s gets cancelled and we are left with these two terms. So we have numerator which is under root 3. When we put s equals to 0 here, we get 3, and when we put s equals to 0 here, we get 3 again. So 3 into 3 is 9 is equals to a. The s would get cancelled with this particular s here. So, and we'll be multiplying s here. So this whole term would go to 0 when we substitute s. So a is equals to 9. So what did we do here? We multiplied the expression e by s and substituted s is equals to 0. So let us do same thing again, but this time we'll be multiplying with s plus 3. So when we multiply s plus 3, this s plus 3 would get cancelled, and then we'll be substituting s plus 3 is equals to 0, that is s equals to minus 3. So let us work on this. Let us work on this side. When we put, we have under root 3 here, s plus 3 would get cancelled. We have s, which is minus 3, and we have s square plus 3. So s square is minus 3 square, which is 9, plus 3 is 12. And similar story, this term this term here would get will become 0 when we multiply by s plus 3. Here the s plus 3 would get cancelled, so will be left with b, and here also we'll be multiplying s plus 3, which would then go to 0 when we substitute s plus 3. So we have solved for b, whose value is under root 3 by minus under root 3 by 36. Now we will do the same thing, and we will so here uh, instead of doing the same thing, we have s square term. So let us substitute s is equals to 1, minus 1, and s is equals to 1 in the expression, so that we can get two expressions in c and d. Then we can solve those linear equations to obtain values for c and d. So when we substitute s equals to minus 1, here we are left with under root 3. So this is minus 1. Here we will have 2, and here we will have 4. So this is minus under root 3 by 8. Now coming to the right hand side, we will have s is minus 1. So we will have minus under root 3 by 9, which is nothing but a. And then we will have s is equals to minus 1. So we'll have b by 2. So which is minus under root 3 by 36 into 2 is 72. Then s is minus 1, so we'll have minus c plus d divided by s square plus 3, which is 4. So if we solve for this, we get under root 3, and 2 into 4 is 8. Oh, we already had that. So this term after solving, so we can multiply uh, both by 8, we'll end up getting minus root 3 over 8 plus, let me write it, d minus c over 4. So these two terms will get cancelled. This implies d minus c by 4 is 0. That means c is equals to d. So we got one condition. Now we will substitute s equals to 1. So we have under root 3 here. Put s is equals to 1. So 1 and 4 and 4 again is equals to a minus, so 3 plus 1 we have 4. So 4 into 36 is 144 under root 3, and here we have plus c plus d over 4. So when we solve this, we will end up getting c plus d is equals to minus under root 3 by 6, and when we substitute c equals to d, we have c is equals to d is equal to minus under root 3 by 12. So let me add up. Okay, nice. So let's add a page here. So now we know our values of a, b, c, d. A was under root 3 by 9. B was minus under root 3 over 36. C and D were minus under root 3 over 12. So now looking at expression E, we can substitute the values. So we have y of s is as under root 3 over 9s minus under root 3 over 36 s plus 3, and minus under root 3 over 12 in bracket s plus 1. We have s square plus 3. So we'll split these two terms separately, minus 3 over 12 s square plus 3 into s, and minus under root 3 by 12 s square plus 3. So now if we take inverse Laplace transform, y of s will become y of t. So under root 3 by 9. So inverse Laplace for 1 over s would be the constant 1. Here we have s plus 3. So uh, the inverse Laplace transform plus for 1 over s plus a would be e power minus a into t. So this here is the cosine term s over s square plus 3. So minus under root 3 by 12, we will have cos of under root 3t, since this term corresponds to omega square. Here, to make this, since we have a 3 here, what we can do is we can multiply by root 3 and divide by root 3. So that we get omega over s square plus omega square. This way we can see that it is indeed the Laplace transform of sine omega t. So this root 3 would get hold on. Yeah, so we need under root 3. Yeah, so Laplace transform of sine under root t would be uh, so if we put omega equals to under root 3, so are we going right?
Yeah,
Yeah. Okay, so
it's correct.
correct.
Yeah.
That's correct, right? So this fellow would become the inverse Laplace transform of sine over t. So we'll be left with 1 over 12. So we wanted to calculate the response of the system, uh, that is then an expression for y of t, which we have found here. Now, moving on to the next question, we want to comment on the stability of the system. So first, let's see what is a stable system. A stable system is something to which if you give an input, or rather if you do not give an input and you start with some non-zero initial condition, it will go towards the output of the system would eventually go to 0. So that is characterized by the poles of the system. That means if the poles of the system are in the left half of the complex plane, that is the real part being negative, then we can say that the system is stable. So we have a big looking expression here, fourth derivative of y plus 8 times third derivative of y plus 22 y double dot plus 24 y dot plus 90 equals to u of t. So now we have done enough Laplace transforms so that we can just directly substitute uh, the zero initial condition. So we get s power 4 into y of s plus other terms which includes y of 0, y dot of 0, y double dot of 0 and y triple dot of 0, all of which are 0, plus 8 into s cube y of s plus 22 s square y of s plus 24y, uh, 24 into s y of s plus 9y of s is equals to u of s. Here, if we want to write the transfer function, we can just take the y of s term common, which is, so g of s is y of s over u of s. We get s power 4 plus 8 s cube plus 22 s square plus 24s plus 9. So this is a intimidating looking degree 4 expression in the denominator, and we want to factorize this to check its zeros. Sorry, to check its poles. So to see the roots of this polynomial, first thing we can observe is that uh, all the terms are positive. So let us try something. We'll try s equals to minus 1 in, to find the roots of denominator polynomial. So let's put minus 1 here. S power 4, so it will be plus 1. Here s cube, that will be minus 1. Then we'll have s square term, so it's positive. Then we have s term, which will be negative, plus 9. So let's try to simplify this. This will end up being 0. So if we take the difference here, it's negative 2. And if we add this 9 plus 1, it's 10, minus 8, it's positive 2. So we end up getting 0. This implies s is equals to minus 1 is the root. Since this is a root, uh, let's do, so s plus 1, we'll write it 4 times to factorize. So we want s power 4 and we already have s. So if we multiply this by s cube, we'll get s power 4 plus s cube. We need 8 of we need 8 of s cubes. We have one of it. So we can multiply here by 7 of s square. That would add us 7s square, and this overall will become 8 s cube. But with 7s, we'll also get 7s square term. Now we need 22 s square and we already have 7. So if we multiply this term by 15 into s, so if we multiply this term by 15 s, we will get 15s square plus 15s. So if we add these two, we would get 22 into s square, which is this term. Now we want to make 24s and we already have 15s. So if we add 9 into, if you just add 9 to this overall would give us 9 into s plus 9. So adding these, 15 plus 9 is 24 into s. So we have s power 4 here. We have 8s cube. We have 22s. We have 24s. We have 22s square, 24s, and 9. So let me write this as p of s. So p of s can be written as s plus 1 in bracket s cube plus 7s square plus 15s plus 9. So we have isolated one factor and we are looking at other three. Now let's see the coefficients again. All of them are positive. So we'll try again. S is equals to minus 1. Let's see what happens. So here s cube will become minus 1 plus 7. S square is positive. Then s is negative. So minus 15 and plus 9. So minus 15 and minus 1 is minus 16. 7 and 9 are plus 16. So this would also give end up being 0, that means s minus 1 would work. So now let us define p1 of s as s cube plus 7s square plus 15s plus 9. We want to get this using s plus 1 as a factor. So if we multiply here by s square, we'll get the s cube term, and we will have s square plus 1, so s square term. We need 7 of them, so we can get we can multiply second term by 6s. So 6s into s would be 6s square, making that 7s square, and we will be left with some 6s. We need to make it 15, so if we multiply the last term by 9, this should work out. So 9 plus 6 would be 50. So p1 of s can be written as s plus 1 So now substituting back here for p1 of s, we get p of s as s plus 1 whole square in bracket s square plus 6s plus 9. If we observe this carefully, this is a square plus 2ab plus b square, where so we can just write s plus 3 whole square. So now we have obtained the factorization of our denominator polynomial. So g of s is s plus 1 whole square and s plus 3 whole square. So if you want to take roots of this, that is poles, there will be s is equals to minus 1, minus 1, minus 3 and minus 3. So 4 values. If we see, all of these are on the left half of the complex plane, and because of this, we can say that the system is stable. So let's just take a look at it one more time. This is the system we have, and we are asked to find whether the system is stable or not. So what we did was we just computed the uh, transfer function. Then we did factorization to write our transfer function in its factors, and then we just looked at the poles of the system, which is zeros, which are the roots of the denominator polynomial. They turn out to be minus 1, minus 1, minus 3, and minus 3. So all of them are negative. That means the system is stable. So let us see why the system is stable quickly. It will take a minute. So we can try it with the unit step input, or well, not necessarily. If we look at the solution of the uh, system, so we'll have y of t into some exponent e power minus at. So all right, let's look at it again. So the solutions for uh, linear ordinary differential equations are of the form a power a into e power minus some alpha t. So if this coefficient of t uh, is negative quantity, which are indeed our poles, minus 1, minus 1, minus 3 and minus 3 here. And if we plot e power minus x, or rather e power minus t, so as t tends to infinity, e power minus alpha t would tend to 0 given alpha is a positive quantity. So the poles here are all negative, so the exponent term will be all negative. So each individual pole will drive the output to the 0, and hence we will get 0 output. We will get a stable system. Similarly, if we look at the response which we calculated in the previous term, we get this under root 3 by 9 because of our input term. And if we look here, we have an exponent term, and the cos and sine terms can be written as exponent terms using complex variables. So essentially, in this particular case, we'll have some kind of sustained oscillatory response because of this cos and sine terms. So that was our tutorial for today. I would be happy to take any questions we have. Shravan, any questions?
No, Pawan, clear. Thank you.
All right, Jayashree.